Section 12.8 deals with what are called directional derivatives. Remember I talked about gradients back in section 12.4. At that time, I simply wanted you to be able to calculate them, and we actually talked about anti-gradients at the same time. And I said to you then that there are two applications of gradients that are really, really important when it comes to applications. 12.8 contains one of them. The next section will contain the other. Visualize the following situation. That you've got a function, f of x and y and z. It is defined in some region of space. Let's suppose it's defined everywhere. If you want something to hang on to, visualize that this represents the temperature at points in the room at which you're working. Now, it is true that that temperature will vary in time, but I don't want that one in here confusing things, right? So let's simply visualize the temperature in your room is not changing in time, but it does vary from point to point in the room. Okay? And suppose this is your eyeball, point x0, y0, and z0. You know that we could calculate df dx. Df dx would represent the rate of change of the temperature at that point going in the x direction. That's what s of x would represent. S of y would represent the rate of change going in the y direction, and s of z would represent the rate of change of the temperature going in the z direction. But suppose you wanted to calculate the rate of change of the temperature in some other direction, say there, in the direction of the vector v, starting at this point at x0, y0, and z0. So you don't want to restrict yourself to only be able to calculate drifts x direction, y direction, z direction. You want the ability to calculate the rate of change of that function, temperature perhaps, going in that direction. The reason would be, well, I want to leave that to later. So what do we mean by that? If you want to calculate the rate of change going in this direction, when you calculate df dx, you're calculating the rate of change with respect to distance going in that direction. Df dy is rate of change with respect to y, distance in the y direction. Df dz, rate of change with respect to z, distance in the z direction. Now we want to talk about rate of change of this function with respect to distance in that direction. So what I've got to do is identify some way of talking about distance. So let's let there be here an axis called the s-axis. So s is a measure of distance from x equal that point there. So let's put s equal to 0 here, and s is distance along that vector v. So what we really want then is the derivative of f with respect to s. That's what I really want. If I want the rate of change of this f function in that direction, I want the derivative of that guy with respect to s. The question is, how do I find it? I don't have f in terms of s. If I did, I could differentiate it. I don't. I propose to do the following. I propose to find parametric equations of that line along the vector v and use those. Now, parametric equations look like x is equal to a plus, let's do x0, because we have x0. x0 plus an at. Y is equal to y0 plus a bt. And z would be equal to z0 plus a ct. That's what parametric equations would look like along this line for some parameter t. But I want things expressed in terms of s. So I'm going to use s as a parameter, not some arbitrary t guy. So s and s and s. Those would be parametric equations of this line where a, b, and c would be any vector along the line, say v being equal to a and b and c. Then those would be parametric equations, and they would be valid. The problem is, with these parametric equations, if I put in s equal to 1, where am I going to be? If I put in s equal to 1 here, here, and here, I'd have x0 plus a, y0 plus b, z0 plus c. Would you agree that would be that dot right there at the end of v? Well, that's fine, except I don't like that. I would like, if I were to put in here s equal to 1, I would like to be at the point here where s is equal to 1. If I were to put in here s equal to 2, I would like to be 2 units away from this point. And that's not doing it. The question is, how do I fix them up so it does that? So what we're saying here is, not any set of parametric equations is going to do for what, to get this. I would suggest the following. I will put into here v sub x, v sub y, v sub z, s, but I haven't done anything here yet, because you could say, well, A is v sub x, and B is v sub y, and C is v sub z. But no, I want those. I'm going to say I want those, v sub x, and v sub y, and v sub z, to be the components not of v, but a unit vector in the same direction as v. Right? So this is a unit vector along here. Right? V was any vector whatsoever that I wanted to go with. This is a unit vector in that same direction. Now, what happens if I put s equal to 1? Then I'll get this plus this, this plus that, this plus that. That will put me right there. All right? Right there, because this guy is a unit vector. That's what I want. So now what I say is, I wanted to differentiate f with respect to s. What have I got? I got f as a function of x and y and z, x is a function of s, y is a function of s, and z is a function of x. Chain rule, here I come. Every time I turn around, it's chain rules. In the last video, it was chain rules for implicit differentiation. Here is chain rules for this derivative. And you'll find in the next section, when we do something else, chain rules again. They're everywhere. So what do we got? F then, x, y, z, s, and s. And we wanted the derivative of f with respect to s. That's going to be df ds. It's going to be df, dx, dx, ds, df, dy, dy, ds, df, dz, dz, ds. But we know dx, ds. Differentiate with respect to s, and you get v sub x. So you get df, dx, v sub x, df, dy, v sub y, df, dz, v sub z. That, if I put into this derivative, I put that point in. I take this derivative, I put that point in. I take this derivative, I put that point in. I've now got the rate of change of this f function going in that direction with respect to distance in that direction. We've got to name this definition. The directional derivative of a function f of x and y and z with respect to distance along the, let's see, along a vector v is this thing here, di f di x, v sub x, di f di y, v sub y, di f di z, v sub z, where vx, vy, vz are the components of a unit vector in the direction of v sub x, v sub y, v sub z. And we're going to give this a notation. We're going to put a big D to stand for differentiation. We're differentiating the function f, so we're going to put it there, and it's in the direction of v, so we're going to put the v down there. So this is our notation, and we're calling it a directional derivative because it's a derivative in a certain direction, and that can be any direction whatsoever. So we now know how to calculate derivatives of functions in any direction whatsoever. Now notice the gradient of f. There's its x component, there's its y component, and there's its z component. But, oh, then is that not precisely the dot product of the gradient vector and the unit vector in the direction I want to go? So here comes my gradient back with its application. To calculate the directional derivative of a function, you take the gradient and you dot it with a unit vector in that required direction. Oh, but wait a minute. When you take a vector and you dot it with a unit vector, what do you get? Back in chapter 11. Isn't that the component of grad f in the direction of v, right? So the directional derivative theorem, the directional derivative of a function f of x and y and z in direction v is the direction of v is the component of the gradient in direction v. So you want to take a directional derivative, all you have to do is take the component of the derivative of the gradient in that direction. Let's do a couple of examples. Example. Find the rate of change of the function f of x and y and z equal to x squared y minus 3xyz squared at the point 1, minus 1, and 2 in the direction tangent to the line x minus y, 2z equal 4, 3x plus y minus z equal to 0, along which z is decreasing. So I have to give you three things. If I want a directional derivative, I have to tell you the function I want to differentiate, 2, the direction I want to go in, and 3, the point at which we're calculating this derivative. And I've given you all of that. There's the function, there's the point, and all this down here is the direction. Now I said this is a line, and you recall from the previous work, that's a plane, and these two planes are intersecting in a line. And do a brief picture, there's a plane, and here's a plane, and here's the line that we're talking about of intersection. So we've got this point 1, 1, minus 1 and 2, and we want to go along that line, and we want to make sure that z is decreasing. By the way, see how quick you are. If I found the rate of change in this direction, what would be the rate of change in the opposite direction? What would be the difference? Well, realize that if you're going to say, if v is that direction, you're doing this. If you're going in that direction, what is v going to be? It's going to be minus what was there. It would simply be the opposite, right? The negative opposite. All right, let's go. How do you produce a vector along this line? We did that back in section 11.5, coming back to haunt us again. What we did was we said, if we took a normal to this plane, we took a normal to that plane, and we crossed them, we would get a vector along the line of intersection. So let's do that. Take the cross product of the normals to these two planes. And the normals are the numbers 1 minus 1 and 2, 1 minus 1 and 2, 1 minus, which happens to be coincidentally the same as that, that's irrelevant, and then 3, 1, and minus 1. 3, 1, and minus 1. So there's the two normals. If we cross them, x component, minus 1. Y component, 7. Z component, 4. Well, that was fortunate, all right, that I put those in that. If I had put these in the reverse order, then I would have got 1 minus 7 minus 4. But notice he said along the way, oh, z is decreasing. Therefore, I do not want a positive z component. I want a negative one. So v then is going to be 1, negative 7, negative 4. That's the direction we're going to go in. So now we've got the pieces. We've got the vector, we've got the function. Here's our formula for calculating directional derivatives. So let's get the gradient, and then we'll substitute. Grad f. Grad f, and we want it at the point 1 minus 1 and 2. So gradient. Differentiating this thing with respect to x, 2xy. 2xy. Differentiate with respect to x, minus 3yz squared. Differentiate with respect to y, x squared. Differentiate with respect to y, minus 3xz squared. Now differentiate with respect to z, minus 6xyz, to be evaluated at 1, minus 1, and 2. Equals. Did I write that down? I don't think I did. All right, plugging in then. This is minus 2. And what do we got here? That's plus 3, 12. That one's 12, and this one was what? Minus 2. 12 and minus 2. 10? Check my arithmetic. I'm putting in, that one is 1. And then we got minus, we got 3 times, that's 3, and that's 4. 12, minus 12, minus 11, minus 11. And finally, multiply these together to get minus 2 and 12. So hopefully I've done that arithmetic correctly. So now we can say the directional derivative of the function in the direction of v is this gradient 10, minus 11, and 12, dotted with a unit vector in this direction. We get a unit vector by taking that thing and dividing by its length, 149 and 16. So we get then 10 minus 77 minus 48 over the square root of 66. Whatever that number is. It's negative. What does that mean to us? The fact that that direction root is negative simply saying to us, at that point, if you go in that direction, this function is decreasing. Same idea as first year, right? The function is getting smaller, smaller, smaller as you go in that direction. Second example, find the rate of change of this function f of x and y and z equal to x squared y cubed plus 3z squared at the point 1, 2, and 3 along the curve x squared plus y squared plus z squared is equal to 14. Y is equal to 2x in direction of decreasing z once again. All right. Somewhat like the last one, but the last one had a line. This one doesn't. So if we kind of, well, maybe we could draw it pretty well, because we would recognize both of these surfaces. That is a sphere centered at the origin. Radius, the square root of 14. This is a plane standing on the line y equal to 2x. So I draw that plane and it intersect, it would produce, it goes all the way around, all right? It's actually a circle in that plane y is equal to 2x. We're supposed to be at the point 1, 2, and 3. So let's suppose there he is. 1, 2, and 3. And we're supposed to be going in the direction of decreasing z. That means this way. So you're at this point. I've got that function. You want to know how fast it's changing as you go in that direction at that point. Well, to calculate directional derivatives, we need three things. We need the point, we got it. We need the gradient, we can find it, and we need the vector v. The vector v, this one here, v. Vector tangent to the curve, basically. When he says along the curve, what it really means is along the tangent vector to the curve. That's the direction. So how do we find a tangent vector to this curve? Well, in the next section, I will give you a method of doing it, but we already have a method of doing that. You want to find the tangent vector to a curve. What do you need? Parametric equations for the curve. Then you can find a tangent vector. So we need parametric equations for this curve. I think probably what I would do is I would put x equal to t, solve this for, and then that would tell me what y is. Put those in and I get the z. So let's put x equal to t, y then is equal to 2t, and z is equal to the square root of 14 minus x squared minus y squared. There. Oh, but that's not quite true, is it? If I solve this for z, what I should have is plus or minus, right? But notice where I am. I'm up here. I'm on the top half of the sphere. Therefore, I don't need the minus sign. So that was lucky. So this then is equal to the square root of 14 minus 5t squared. And that's what we can see. A tangent vector to curve is, call it t, we get it by doing dx dt, dy dt, and dz dt. dx dt, 1, dy dt, 2, dz dt, a little more difficult, about minus 5 over the square root of 14 minus 5t squared. Out is coming, down is coming a half, and out is coming a minus 10. Oops, I think I need a t here. How does that look to you? From the derivative of that with respect to t. Bring down the power, that's a half. Out is coming minus 10. Not. Okay, I like that. Right? Well, okay, so at the point, what's the point? 1, 2, and 3. What is t? At that point. So I want to go to the point 1, 2, 3. So we need the value of t that gives 1, 2, 3. Well, if x is 1, then clearly t is equal to 1. And so we're going to take this thing and put in 1. 1, 2, minus 5 over put in 1, the square root of 9, 3. So there then is a tangent vector to this curve at that point. Now what I mean for the directional derivative? I needed it. Point, I got it. 2, I need the gradient. And 3, I needed a unit vector in the direction. Here's a vector in the direction. I need a unit vector. Could I also say, or multiply by 3, 3, 6 minus 5 is also tangent. I'm going to turn it into a unit vector anyway. I'd rather turn this into a unit vector than that. Right? So now we need the gradient. So let's go get grad f. Grad f at point 1, 2, and 3. Gradient is 2x y cubed. That's it for the x term. Y derivative, 3 x squared, y squared, and the z derivative, 6z. To evaluate it 1, 2, and 3. Substitute. 1 here, 3 there, how about 54? Comma. 1 going into there, 2 going into there, 12, and 18. So there's the gradient at the point. So now we can see the directional derivative of the function in the tangent direction is this guy, 54, 12, and 18. Oh, one thing we didn't check, it says in the direction of decreasing z. Oh, that's okay. Notice we have a negative z component, so this is the one that we want. If that had said increasing, I would have changed these signs. So we now need the unit vector, that's that one. 3, 6 times 5, divided by its length, the square root of 9, 36, and 25. So I need you to do that dot product and get the final answer. So there's 2 examples then of calculating directional derivatives, and they brought in material from chapter 11. Remember I said in chapter 11, I'm preparing the way for things that I need in chapter 12. And here, first example needed that material on planes. This one needed parametric equations from the curve. Theory. The gradient grad f of a function x, f, is the direction in which f increases that's going to be good. F increases most rapidly and grad f is, and the length of grad f is the maximum rate of increase. This is probably the most important property of gradients. If you take the gradient of a function, that direction, the gradient direction, is the direction in which the function increases most rapidly, and the rate of increase in that direction is how long the gradient is. For instance, you want to talk about heat flow. Now, you're going to be involved in things called partial differential equations. But all heat flow is based upon Newton's law of heat flow. And what it says is, heat flows in the direction in which temperature decreases most rapidly. And that, you know, I could have been famous if I'd been born earlier, because that's just logical, okay? If the temperature is varying here, which way is heat going to flow? It's going to flow from hot to cold. And that's what Newton's law of heat flow said. It will flow in the direction in which temperature decreases most rapidly. Well, gradient points in the direction in which it increases most rapidly, so minus gradient is the direction in which it decreases most rapidly. So if you take the gradient of the temperature function, heat flows directly opposite to it. And all heat flow is based upon that law. It's all got to do with gradients. Right? That's the basis of heat flow. All right, proof. I gave two proofs in the book. One I kind of illustrated geometrically, and then I talked about algebraically. I'm simply going to talk about algebraically. Is this true? The directional derivative of a function f in a direction v is grad f dot v hat. It's the component of the gradient in the direction of v. So you did the unit vector, right? But, oh, you know about dot products. Isn't the dot product the length of the first, the length of the second, the cosine of the angle between them? Theta angle between grad f and v, or v hat, right? But that's 1. So unit vector's length is 1. So if you said, I want to vary the v vector so that this thing turns out to be as large as possible, right? You've got the grad f vector here, and you've got the v vector here, and you say, what direction should you be so that this thing is as big as possible? And theta's in here, and the answer is, make this thing as large as, you can't touch that, make this thing as big as possible. Well, what's the biggest value of cos theta? Answer, 1. When is it? When theta is 0. Largest when theta is equal to 0. In which case, the directional derivative is that. Right? So maximum, direction for maximum is when theta is equal to 0. That means you're along here, and how big is it along there? There it is, and that's exactly what the theorem said. That the gradient points in the direction in which the function increases most rapidly, and the rate of increase in that direction is exactly how long the gradient is. Now, you might have asked the question, so logical. I started out this class by asking about the rate of change in a function going in a certain direction. As soon as you say rate of change, if we reflect back to first year, when you talked about derivatives were defined to be a limit of f of x plus h minus f of x divided by h. That's the way we really define it. The question might be here is, could you define directional derivatives the same way? By saying, oh, go evaluate the function at a point plus a little bit in the direction b, subtract it there, divide by the little bit, and take the limit as a little bit goes to 0, would you get the same result? And the answer is yes, you would. And I talk about that in the book, but I don't think I want to talk about it here. So we just kind of avoided that by doing what we did here. So that's it for directional derivatives.